has it's an endless line. I mean, it runs on both sides of the flooring, and then it has a turning block here at the bottom of the mast, and then it comes up. Let's see. I'm trying to remember this. It comes up. This comes up on both sides. Goes to a single pulley here. And this one then goes to another line. Wait, hold on here. Now this one. Let's see. Hold on. It's a 16 to 1. It has two double blocks that are cascaded.
Yeah.
And so instead of having like just a whole bunch of single blocks, it has cascading blocks. And so there's only one line that goes to the pulley on the boom, but then it's a double, and then it's a quad, and it goes down here so that you, and it's incredibly powerful. Man, I can bend the tip of the mast back about 2 feet with the boom bank. And I use it mostly for, boom banks typically used for twist control, correct? But I use mine to correct the draft of the main, because it's like a downhaul on a windsurfer. You do that to flatten the sail. You downhaul like the devil because it causes the mast to bend and you flattens out your main. So on my 470, I use a lot of Vang. It has the Traveler as well, so you can control twist of the Traveler. I have to put a lot of boom bang on mine. I don't like it. Sometimes lighter, you want to have a lot of twist on top, right? And I can't do that because it looks bad. But yeah, sailing a sloop rig, fractional rig sloop rig without a Vang is painful. Going downwind, really painful, right?
Yeah, that's what we figured out yesterday.
Wow. Yeah, that's.
But yeah, I mean, we can still take the boats out. It's just really annoying to not have Vangs.
Apparently, one of them doesn't have hiking straps.
Yeah.
Oh, that's dangerous.
Yeah, that's.
that was the one that I went in. We went out and then
Just
we were
hook your feet under the trunk.
That's what we did.
We have to go so we can cannibalize.
Oh yeah, but we could.
We should just
I'm gonna be
have
fixing
6
that boat
boats.
tomorrow. Like I'm gonna be fiberglassing it tomorrow.
Oh, really? Hell yeah, dude.
Yeah. No, we just need to get that fixed. But like, you can't keep cannibalizing it because that would.
Yeah.
Well, you have more boats than you need, I think.
Yeah.
Well, that's supposed to be our fun boat.
Yeah.
We'll be captain the Spinning rig.
Alrighty. Okay, so we left off with the guarantee that we all know the parts of sail this morning, this afternoon. Who knows all the corners and the edges? Who doesn't?
I was in here last week, and I feel like I know most of them.
Yeah. Typical mainsail.
Yeah.
This part is,
The head.
you knew this.
Yeah, I didn't know that. That's the only part I know. And like the battens.
Okay. Okay, this is the head. Okay, this point here, what is that one? You see that? So you don't know any of the parts, any of the ones? Are you new here today? You here last time?
Yeah, I'll video it.
Really?
Yeah. That's alright.
Okay, I'm sorry. What's this point here?
Is it the lock? Wait, no, I take that back.
So, pardon? Yes, it's the tack.
Already my amazing.
Well done, well done. So you were here, just weren't listening. Okay, and so these are really important. And remember, I'm showing you a mainsail, but these are the same points on any three-cornered sail. And I struggle to say triangle because obviously most spinnakers are not triangles. But they have 3 corners. Okay, so that's important to know. And then you said left, right?
Yes.
What is the left?
Is it the side?
No, I asked the question, you provide answers. What is the luff?
Yeah, is it the, or it
No,
is,
do not start it with a question. Say, it is.
it is the side of the sail that connects the head to the tack, or the, what's
You're
that?
saying this, you're saying it's this side and say it here, the
That's
left,
what-
right?
Yeah, that's what I'm saying.
Who agrees with that?
Okay.
What does the word luffing mean when a sail luffs?
It's like,
Yeah.
Can I change my answer?
No, I agree with that.
Oh, okay.
This is good. I just want to make sure you guys knew. I go, this is the luff. It's also called, on sails, they have an IJ. You remember those numbers? You see on boats, they'll have an IJ, P, and E measurements. And the I measurement is going to be the height of the luff, the length of the luff. The J is the length of the boom. The P is the length of the foredeck, and the J is the height of the forestay. So when they give rated areas for boats that are not one design, I talked about this before, they only rate the area, the triangular area. That's the rated area. What's this part here? What's this part called here?
The roach.
The roach, right. Okay, and then the back of this thing is called?
The leash.
Yeah, that's right. And then, of course, this is not the ankle, but this is called the cankle. Anybody know what cankles are? If you're politically astute, you know what cankles are. This is the foot. Okay, so we're going to talk about sail rigs today. Starting off sail rigs, then I got some really cool engineering we're going to talk about later on. Part of learning how to sail is to be able to talk to other sailors and to be able to not embarrass yourself in front of sailboats. And so sailboats have all sorts of different configurations. And there's different ways of categorizing sailboats. I'm going to categorize them by sail arrangements. So here are some definitions. How many people know what all 5 of those configurations are? And remember, we're talking about, these are types of sailboats. Good. These are types of sailboats which are determined by their sail configuration, their driving configuration. We've already mentioned catboat. You remember what a catboat is? If you have a 420, it's a catboat. If you have a Sunfish, it's a catboat. If you have a 470, it's a catboat. If you have a Hobie 16, it's a catboat. If you have a J-boat Endeavor, it's a catboat. What's the distinction of all those boats I mentioned? How many masts do they have? A single mast. How many sails? So here we go. So here they're defined by the number of masts and the number of sails. Now sails, we're talking, these are called working sails. In other words, what is the normal complement of sails you would have for any direction? A lot of boats will have additional sails you can add for certain specifics. Okay, so a catboat has 1 mast and how many sails? No, so I misled you there. 420s are not catboats, I'm sorry. What am I thinking? That was, so you knew that. And you say, oh, I'm not going to say anything, so they dig deeper and deeper. But a Sunfish is, a Laser is, a Force 5 is, a Flying Fish is, yeah. How many sails does a Sunfish have?
1.
That's right. So a catboat is a single-sailed vessel which has obviously 1 mast to hold the sail. Technically, I guess if you had a kite-driven sailboat, I guess I would still call it a catboat because it has 1 sail. So this is the big thing here, this 1 sail. Okay, so now then, I'm sorry about that misstatement I made earlier there, but because that wasn't correct. What kind of a boat is a 420?
Sloop.
Yep. How many masts?
1,
How many sails? Working sails.
2.
Okay. And this is always the case with the sloop. Oh, there's another thing, I can put it, okay, never mind, I'll keep putting it. There's yeah, I need to put another boat down here, I'm sorry. Another type of boat, I should know this because I had one of these. Okay, so now I ask, who knows what all these are, including a cutter? You know, okay, you know what a cutter is?
I know what a cutter is,
You do?
but I don't know.
Okay, like a lot of these things, cat is lots of different things, but
Yeah.
by basis of sail driving, this is what it is. Cutter can be a lot of things, but if you have a cutter rig, it means a particular thing. Doesn't mean a shape of a hull, doesn't mean it's an ice cutter or whatever, it has, okay, so, schooner. What's a schooner? How many masts?
It has at least 2 masts, and the largest mast is the aftmost mast.
Ah, close, but not quite correct. It means that the foremast is going to be equal or less than in length to the aft mast. Because if they're both the same size, it's a schooner rig. This is the mast it's going to be. This is what it means. Now it can have a whole bunch of variety of sails. Typically, they will have you'll have a main sail on each mast, and you'll only have at least one head sail. So typically, you'd have at least, if it's a 2-masted schooner, you'd have at least 3 sails, working sails. But oftentimes, you'll have a lot of other sails which could be intermediates to it. But the most important thing is it's always going to have at least, and typically a schooner is typically 2 masts. Most of them will have just 2 masts, but you could have more than that. And it does mean that if you have 2 masts, that means that the foremast, the one further forward, will be at least equal in height. Sometimes it will be slightly smaller than the aft one. But if you have both the same size, it's the schooner. Now, let's skip down to ketch. What's the difference between a ketch and a schooner? And you'll see a lot of ketches are schooners are not so popular these days in terms of cruising boats. I can't think of any new boats that are made of schooner rigs. There may be some, but they used to be more popular. They're particularly good for trade wind sailing because what you need to get you need a lot of project area without a lot of height, and so they were used to that. Okay, you had something?
Yeah, just the catch and a schooner.
Yeah. Okay. What's the difference catch?
The aftmost mast is smaller.
Yep. So a ketch is going to be 2 masts, and so it can have a bunch of different sails there, but it means that the aft mast, what is the aft mast called in a schooner or a yawl? What is it called?
Mizzen mast.
The mizzen mast. And so so this means that the mizzen mast will be less than, always shorter than the foremast, or actually we'll call it the main mast in this case. That's typically what they call it. Okay. Now, what's the difference between a yawl and a ketch? You know, yeah, what is it?
Does the yawl have the aftmost mast behind the steering wheel?
So here is, for example, this could be. Oh gosh, I did it. Okay. So if the mast were stepped like this goes up higher. This would be a catch. If now on the other hand, if this mast was actually, if there's a rudder post here, this is where the rudder post is. This swings off. And typically in a yawl, you have a different body shape. You'd have a stern like this. You have an inset rudder like this. So the rudder post right here. Then the mizzen mast would be set aft of the rudder post. Now you can't always tell that from looking at a boat from distance. And so traditionally, what you would find, the yawl is going to be the mizzen is aft of rudder post. Where the rudder post is the actual, that's the pivot point for the rudder. And so you have a relatively large main and a very small mizzen. What is the mizzen primarily used for? Because it typically, it's going to be much smaller than the main mast. What's it, in a yawl, what's the mizzen used for? You know? Typically it's also cut very flat, almost no draft in it. It's mostly for steering. It's an air rudder, if you will. And it's used to balance the boat. It provides you, in fact, to windward, most people won't even bother raising it. It's just a source of drag when you're going to windward. But off the wind, it can contribute. It's also very useful when you're at anchor. If you've ever been on a cruising boat, who's been on cruising boats at anchor and had the hull do sailing? It's really annoying. You get a lot of breeze, like in a trade wind, you anchor. The sides of your boat will catch the wind, it'll develop a little bit of lift, it'll go like this, and then it snatches the cable, and it snaps back like this, and the chain continues doing this stuff. And the boat will yaw about 10 degrees. It's really annoying. And so if you put a mizzen back here, it acts like the feathers of an arrow. It keeps the boat from doing that. And so it's also used for that. But understand that on a yawl, the mizzen sail is not designed to provide drive. It's designed to provide balance, sail balance. We'll talk a little bit later on today about summation of moments and how this all affects the balance of the boat. But it's mostly for steering. On a ketch, it's definitely a driving sail. In fact, generally speaking, ketches and schooners are your fastest boats if you're doing broad reaching. They're, you know, when it gets right down to it, the driving section of a sail is your luff. That's where the leading edge of sail is where your drive's coming from. So the more leading edge you have for the same sail area, the more drive you can really get. So if you split it up with having lots of leading edges of sails, like they do with multiple bits like this, then you'll have a better windward boat, or better lifting boat. The problem for going upwind with any of these multi-masted sails is what happens. Where is the boom? If you've got a really close hauled boat that can really go to windward well, how close is your boom to center line? When you're really hardened up and you're trying to go to windward, how close do you suppose it is to center line? Because remember, the closer you're going to wind, the more you have to pull your main in to get that angle of attack as close as you can to keep going down. If you look at most modern boats which have full hoist jibs, unlike a 420, which is like a fractional jib, the jib, the leading sail of a 420 or a 470 isn't really as significant as it is on a boat which has a full hoist, a very large jib. On a boat that has a large jib, and often the jib is called a genoa, which is going to be equal in area, if not bigger than your main. The main will be sheeted all the way to center line when you're going upwind. That's because when the wind comes over, if you think about this, here you have this big jib like this, and then you have your main here. If the main was sheeted at the same angle as your jib, so here's the angle of the jib, here's the angle of the main. The wind coming here would backwind the main, and the main doesn't work. And so you'll find out that in practical situations, the jib does alter the apparent wind direction to the main. And so because of that, when you have the jib out like this, the airstream is going like this, it's flowing like this, but now X is going like this. So it's changed its heading, which means that in order to get the same angle of attack from the main, you have to have it sheeted in harder. Because it's no longer dealing with this angle, it's dealing with this angle. Because the jib has already changed the direction of the wind. And so that means that on a really close haul boat, you're often going to have the boom almost on center line. Now if you put another sail behind it, if you have like a schooner or something else, okay, so now the wind coming up here has been shifted again like this. So now you don't have any angle of attack left for the second sail. And so you'll find out that ketches, yawls, and schooners do not go windward like a catboat or a sloop boat. because the second sail or the third sail is going to be basically worthless. Most people, these boats just will not go to windward like a sloop or whatever. Now, what's a cutter? What's the difference between that? You know what a cutter is? What's a cutter rig? How many masts on a cutter? One. In fact, cutters often operate like sloops, but they will have 3 working sails, not 2. The difference between a cutter and a sloop is, and you can tell this from a distance actually, typically on a sailboat, first off, if it is a cat rig, you'll find that the mast will be maybe here. So this would be like a cat rig. Now then, if I go to a sloop, you'll find that the mast is further aft. You'll move the mast to be aft about here, because you're going to have a jib and a main, and you want to keep the center of effort roughly in the same position. When you go to a cutter rig, the mast will typically be about in the middle of the boat. It'll be that much further, about here, and you will have the forestay, but you'll also have a baby stay, and you'll have your main out here, and you will run 2 jibs, one off of what's called the baby stay, and then another one off the forestay. And so it runs with 3 sails. It's called a cutter rig, and it gives you 3 long luff areas for developing lift when you're reaching. On the very first day that I was here, I gave you that little slideshow about some of the boats that I've owned. The 52-foot boat that we cruised in the Caribbean and Atlantic in was a cutter rig, and so in trade winds, when you're reaching, you'd have all 3 sails up all the time. But if you're going to windward, you would take this sail down, the small, it's called staysail. This would be called the jib or genoa. This one is called the staysail. And then, of course, this is the main. Now, there's a huge advantage for cutter rigs if you're going offshore in conditions that are nasty. What happens? We talked about the fact that the forces on the sails go up by the square of the apparent wave velocity. And so that means that if the wind doubles, you only need 1/4 as much sail area to develop the same force. But we can't usually do that on some boats. On a cat rig with 1 sail, what can you do? Some you can kind of roll up a little bit, like on my Hobie. I have a Hobie kayak that has a roller furling mainsail, so you can actually roll it up a bit. But they don't sit very well when they do that. But it's not very easily done. On a sloop, sometimes you'll have reef points. You can lower the main you would have points here. This main could be lowered down to say like this. But if you only have 1 jib, the jib's still going to be up there, which means the center of effort moves forward, which is sometimes okay, because we'll discover later on that the more a boat heels, the more you want center of effort forward at any rate. But on a cutter, you simply start reducing. The first thing to do, as winds develop, the first thing I'm going to do is take the staysail down, run just with the jib and the main. The next thing I'm going to do is I'm going to reduce the main. I'm going to drop the main down to a reef point, take this jib, roll it up, and then put a staysail on, and now I have a perfectly symmetrical small sloop rig. Suddenly I just have an area here, and it behaves perfectly well, and I reduce the area by over half, but I also lowered the center of effort so that the boat doesn't feel much anymore. So they're really, really good to vary a lot of different winds. We were up in our boat, we hit 63 knots of breeze at one point. Now we weren't sailing there, we were anchored. The most we ever sailed in was 52 knots of wind. But I went with a staysail and a double reefed main, which is about this size, and the boat was totally capable and perfectly safe in 50 plus knots of wind. Now I challenge any other boat to be able to do that, 50 knots. That's, again, that's like 25 times more force on the wind than it would be at the normal, 10 knots of breeze. Okay, so cat boats, one sail, one mast. Sloops and cutters only have one mast, but they have either two or three. The difference between a yawl and a ketch becomes more difficult sometimes because it's oftentimes boats will not have it will be not clear where the wheel is or where the post is. So generally speaking, if you look at a cutter, it means the mizzen will be less than 50% of the main mast height. Main mast. So if you look at it from a distance and you see that it's less than half as tall, it's almost certainly going to be it's almost certainly going to be a yawl. If it's more than 50%, it's going to be a ketch. And so if you look at a distance, you see them on a dock, and their mast like this. Okay, that's a catch. And when you get down like this, that's a yawl. You won't find very many yawls these days. So mostly what you're going to see are sloops and catches. And cutters, if you're talking about boats that are designed to really cross oceans, they'll often be cutters because it's so easy to balance. And it's also the problem with putting a very small jib on the forestay and a reef main is that means you have to walk out to this pointy, dangerous part in the middle of an ocean to do anything of that. When you have a cutter, you are still inboard of the pointy, dangerous part, which may be going underwater occasionally. And so it's a much safer boat to work on too in a big storm. Okay. Okay, any questions about those types? There's a whole bunch of other things. You can talk about brigantines and brigs and all those kind of stuff, which are the typical square sail boats. But these are what you're going to see, and you should be able to recognize those from a distance. Okay, so again, these distinctions here are all based upon the sail rig. You can also distinguish boats based upon their hulls. Okay, and I think this is pretty clear. We certainly have, you have a monohull. Which obviously is one sticking hull. And there's a whole bunch of different things we're going to talk about, different types of those. If you have two hulls, what's this called? Two-hull boat. It's either called a catamaran. This is twin hulls. Or it could be called a proa. Anybody know what a proa is? A proa is when you have two hulls, but one is much, much smaller than the other. This is the typical Polynesian cruising boats, were proas. They would look like this. They'd have a canoe, basically, with the sail on there, and then they'd have outriggers here and a small thing here. It's called an ama. This is called an ama, which is the smaller hull. This is the main hull here. And that's a proa, where it looks like just like a monohull, but it has a balancing arm out there with a small flotation. There'd be no sails on that. Now, a catamaran, they're the same size. On a proa, they're not. And 3 hulls is called
Trimaran?
trimaran. Now, trimaran is 3 hulls. Okay. Of these boats, which do you think are fastest? What would you think? Or why would you want one versus the others of these? Which is the most stable? I mean, stable meaning which one would heel the least in a breeze?
A trimaran?
No. Catamarans. Catamarans are the stiffest boats. Stiff to the point where they can become dangerous. Meaning that when a boat heels, either you, being the crew, or ballast down below, tries to straighten it back up. There's a righting moment. When a boat heels, you lean out, you do the righting moment, it comes back up. On a well-designed cruising boat, you want it to have, without you moving your body, you have enough ballast down there, so no matter how much it heels, it always has a positive moment to come back up. In fact, if you look at most cruising boats, when they test them, they will take them all the way upside down and then actually go under, and they still have to demonstrate positive riding ability to about 120 degrees. And that's so that in a wave, you get knocked down, it will come back up. That's important. A catamaran takes a lot more to get heeling. But beyond about 45 degrees, it has no longer a positive riding moment. It is more stable this way than it is this way. In fact, the most stable position for a catamaran is this way. This is the reason why catamarans are not normally considered incredibly seaworthy, because they are much more stable upside down. Once they're upside down, they're very hard to right, because not only is the weight down now below, their mass acts like a keel. It's down below. There's no weight on the top. There's no keel. But also just getting the wave, giving the sail to come up through the water is really tough. Even on a monohull, it's hard. Once you turn a turtle, it will come back up, but you can do it. But so these are the stiffest boats in terms of the least amount of heel for the wind, but they will never have positive riding beyond about maybe 45, 50 degrees, and that's it. Trimarans are actually a compromise, because trimarans are going to have a fairly large main hull, but then we'll have another AMA on the other side. And so these actually, when properly designed, they may or may not float on just one. So they're stiffer initially, but they still develop that heel, which is an important thing for the sailor to know when you're being overpowered. If you have a boat that doesn't heel, when you don't know that you're about ready to break things, because you don't feel that feedback of having too much wind on there. And have you ever driven a Miata? Mazda Miata? Miatas are known for having very poor.
Wow.
Miata's a great little car. Mazda makes it. It's one that it's stayed true to its concept of being a lightweight performance car, very light and agile. But they roll a lot. They're not very stiff in the roll. And they do that particularly because it gives the driver feedback about when you're ready to lose it. If you ever drive a car that has incredibly stiff anti-roll bars, it'll break loose suddenly. You don't notice it when you've come to the limit. When a car starts to roll, you think, oh my God, I think I'm approaching the limit. This thing starts getting the tires squeal and all this kind of stuff. And so the feedback on a Miata is that they're a very safe and controllable car to drive, especially like an autocross, because you can feel when you're at the limit. You get these warning signs you're getting at the limit of the traction, because you feel the car roll. Same thing happens with a trimaran. You'll feel it starting to heel. On a monohull, the more wind you go, the more it heels, but you know that. You know that, okay, I can tolerate 30 degrees, and beyond that, I got to reduce sail. And you know you're getting that limit. And plus, monohull will always have positive riding moment. Catamarans will not. Trimarans are also more stable upside down, but most trimarans will give you a lot more warning. They'll be stable probably to about 80 degrees. And so typically monohulls were what you always saw the major ocean going vessels were, because they were safer, and they actually have more volume in them too, because they rely upon weight for ballast, not form stability. In monohulls, and in fact there's a couple of different things we can talk about. There's things called displacement, and there's things called planing, and there's things called foils. These are all different kinds of monohull construction. When we talk about boats, we don't talk about the weight of a boat. You do, actually, if you talk about the weight of a boat, you're a rookie. You talk about the displacement of a boat. What is the definition of displacement?
The amount of water or fluid that the object is placed in the water.
When it's sitting there.
Yeah, exactly.
And if you were to measure that, Archimedes says, well, that's the weight of your boat. You well understand Archimedes' rules about that? That the amount, remember this is the famous thing about he's trying to weigh some gold or something, but Archimedes says that something which is floating displaces exactly the amount of water in that cavity where it's floating that it weighs. So, here's another little question for you guys. if you heard, then don't give the answer away. You're going across a lake which has got and you've got a big suitcase full of bowling balls. And you're going across the lake and you drop your suitcase with all these bowling balls and it goes right to the bottom of the lake. You come back to the shore, and before you step foot on the shore, you say, oh my gosh, look at the water line has stayed the same, the water line has lowered, the water line has gone up. Based upon you just losing that suitcase full of bowling balls. What happens to the height of the water in the lake by the fact that you lost that? Okay, you say it goes up.
Because wait, you dropped it into the
Yeah,
water.
you dropped it. You're sitting there, and you're sitting here on your boat, and you're in this pond, and you look at there's a water line, but you have a little measure there. Now then, you drop these bowling balls off. What happens to the water line? Does it go up or down?
It stays the same.
Or it doesn't change?
It doesn't change.
Okay, who says it doesn't change? Okay. Who says it goes up? Who says it goes down? Tell me why it goes down.
Because the full mass of the bowling balls is able to keep it floating. So that's what we see at the bottom.
Tell me why it goes up. Yeah.
I was gonna say the same.
Let me rephrase this thing. Every time a ship is sunk in the ocean, does the water line go up or down? The ocean level go up or down? Same story. Every time a ship is sunk. Now, I'm not talking about a submarine. I'm talking about a ship. And hint, if a submarine sinks, it makes no difference to the water line. But if you have an aircraft carrier out there and it gets blown up and sinks, does the water line go up or down?
I guess like like tiny.
Okay, I pick on you, Alex, because it does go down. When a weight is being suspended on board a boat, Archimedes says it displaces, the amount of water it displaces equals its weight. When it sinks, the amount of water it displaces equals its volume. So if you sink something which was afloat in your boat, and now it is in the water and it weighs more than water, that means you've displaced less than you did before. Because you're displacing the weight of the boat, but instead of displacing the weight of the bowling balls, you're only displacing the volume of the bowling balls. And because they weigh more than water, they sink, and therefore you're not displacing much water, so the water goes down. Everything that sinks into the ocean that was floating makes the water level go down. Interesting question. I used to get that for a high school course I used to teach. And then people figured out that you could ask Google that and it would answer it. So I kept changing it to, you were floating in that Jupiter moon that's full of liquid, what is it? I would change from water to, what is it? Is it supposed to be a sea of something right there? But at any rate, so I changed that to the point where Google wouldn't know what to do with it. Okay, so that's a displacement boat is one that always is sitting in the water. It always displaces the amount of water which is equal to its weight. A planing boat, a 420 is a planing boat. So is a sunfish in certain conditions. What happens to the amount of water you displace on a planing boat? What's the difference between a planing boat and a displacement boat? The difference is the fun. Displacement boats never go faster than their hull speed. We're going to talk about that. Oh, do you know what hull speed is? Do you know what hull speed is?
So,
If I told you that that it's very, very secret how fast our aircraft carriers go, or how fast a Russian aircraft carrier can go, but you knew the dimensions, what would you say to me? What are the dimensions of an aircraft carrier? Roughly 1,000 feet, right? Waterline length is 900 feet. How fast will it go? You got to think, guys, new hull speed. How fast will it go? I can tell you within 1 knot how fast it'll go, without knowing how it's powered. Because that's the definition of hull speed. I mean, I can tell you it can go slower than that, but I can tell you the maximum speed it can go. New submarines, they must have a lot of drag underwater. Do they go faster underwater or on top of water? Submarine.
On top of the water.
Nope. Because on top of the water, they're limited to hull speed. Underwater, they're not. So it is really important. There's no way of knowing how fast a submarine can go. That's the reason why it's incredibly secret. Although people know basically this kind of. But they'll go roughly, most submarines will go, well, attack submarines will go 2 or 3 times faster underwater than they can on top water. At least 2 times. And especially nuclear attack submarines. They'll go much faster than a floating boat can go. Because they're displacement boats. If you don't, okay, we're skipping ahead, but hull speed of any boat, I might as well give you something we're talking about. Hull speed is defined by this formula, which works out quite well. Hull speed of a boat equals 1.34 times the water line when this is in feet and this is in knots. So, for example, your aircraft carrier is going to be 900 feet. Oops, I'm sorry. Square root of that. 1.3 times the square root of that. So 900 feet, take square root of that is 30. 1.34, 43 knots. That's how fast the aircraft carrier can go. Look at a 420. A 420 water length is about. Let's look at something that's easier to work on. Let's look at a hypothetical 16-foot water line boat. I'm trying to think of something like that. 505 is roughly 16 feet in water line, 18 feet overall. So that would be that would mean 5.3 knots would be the hull speed of like a 505 or 470. A little bit's like 4.5 knots, 4.8 knots like that for a 420. But they go faster than that. How come? They go faster than that. But a aircraft carrier, I guarantee, cannot. The reason why I do is because they're a planing boat. A planing boat no longer displaces the water equal to its weight. It gets hydrodynamic lift, like a water skier. It pops up. And so that's the reason why they can go much faster than that. Anybody water ski? When you get towed, when you start accelerating the ski boat, what happens to the bow when you start slowly going up? It does this, right? And then all of a sudden it does this, and you start going faster, right? Up to this point here, you're doing hull speed. Physics says that a wave propagates through a medium depending upon the velocity of propagation of that medium and the speed at which it's traveling, and speed at which it's traveling. So there's a frequency and speed that all correlates there. It turns out that the faster a wave travels, the longer its wavelength is. The wavelength is directly proportional to the speed. And so what happens is that when you start pushing a wave, you make a wave, and then you're going slowly, so there's another wave, another wave, another wave. As you go faster, these waves get further and further apart. Hull speed occurs when the second wave now is at the back of your boat. Because that means if you try to go any faster, what happens? Your boat's going uphill. That's what happens in a ski boat. You're idling along, no problem. You put a little power, all of a sudden the bow starts rate because you're going up bow wave, but the stern wave is no longer there. And you add more and more and more power, and all of a sudden it starts to plane. And then it levels out. It takes a lot less power here than it does to do this. No atomic submarine, no matter how fast, how much power you put in, will ever be able to plane a aircraft carrier. It'll always be displacement mode, which means they can never escape that stern wave. And so that's the reason why we have planing monohulls, because they can break through that. They have a flat bottom, so it develops a lift and you can go up there. The final thing is a foil suspended. And if you don't know about that, almost all your high-performance monohulls these days, and some multi-hulls, are going to be foil suspended. I just watched the Swiss GP, Sail GP last night. They raced last weekend, and there's very, very light air there in Lake Garda. Not Lake Garda, it's in Geneva. There's the big lake there, Lake Geneva, I think it is. And still they're doing, they're 50-foot long boats. Hull speed wise would be 7 times 1.3, about, maybe hull speed maybe 10 knots. Yet they're doing typically about 30 knots, because they're raison foils. And of course, the record for those now is over 65 knots. And so they're not planing. They're using underwater foils for that. I wasn't planning on getting this thing, but now I understand that there is this figure here has been empirically developed over the years, and it's one of those horrible engineering formula that you can't do a units analysis on. This only works if you use this in feet, and it only comes out in knots. So don't be confused. Don't try to figure, well, what are the units for this 1.34? I guess it would be, I don't know, the square root of feet. I mean, it'd be knots divided by the square root of feet or whatever it is. But but this does work out. Now, by doing clever things, you can sometimes change this from maybe 1.2 to maybe 1.4. This could range a little bit, but that 1.1 1/3 is a good way to look at all this. And you'll discover it on your small dinghies that right at about 4 knots is when they will move with no air, almost nothing. It takes almost nothing to go 4 knots. It takes quite a bit more to go faster than that. And lightweight boats which have a flat bottom can often, they almost all can go planing, which is an amazing advantage. Oh, yeah, I was getting into the engineering stuff. We'll introduce it. And we talked this before about static analysis of boats. Let's just look quickly here. We'll have to continue next time. This is such an interesting and important topic. If you look straight down on a boat, just draw it like this. Okay, and so we're going to talk about a cat rig boat with a single sail. Okay, we're going to draw a sail like this. So we know, we've talked about the wind coming like this. We know that there's a center of effort here. We talked about this the very first day. That's basically going to be, the center of effort is basically going to be in this direction here. The sum of forces from that sail is going to be in this direction here, which means that there's going to be a component that's going to be going forward and a component going backwards. Now, we know also that there's going to be a underwater foil that's also going to be not dealing with this apparent fluid, but apparent fluid coming from this direction, which is going to be the water. And because we know it has to have a little bit of, first off, we know from the sum of forces, we know the sum of forces, this is x, and this is y direction. We know the sum of forces in the x direction must be equal to 0 if we want things to be a static equilibrium, which is what they will be. Which means that there must be, if there's a side force here, there must be equal force here. These two forces must be equal in order for the sum of forces in the x direction to be equal. Now then, if we look at sum of moments about the z direction, and of course this is x, y, that z is coming up positive, z is this direction here. We can look at this in several different ways. Let's ignore these two force components for a moment and just say, remember, we also have another foil here, which is the rudder. We know when we take sum of moments, engineers know this, we can pick any point we want to, sum moments around. So let's pick this point right here. And the way I've drawn it, guess what? If I ignore these two components here, this is the force of the wing, and this is the force of the keel. And if we look at this, think moments about that. Well, this one goes straight through this point that I picked, which means there is no, this would be equal to 0, which means this would be Fw times some d1 plus Fk times d2. But you discover that the d2 is the amount this force is displaced from that arbitrary point I picked. In this case, guess what? This means that if this all works out, that means that this force must equal this force. Excuse me. It means that there's no net turning force, which means if I were to put a force on, let's see, if I wanted to put a force here, it would be imbalanced and the boat would turn. So in this case here, there is no force here at all required to go straight. This is called a neutral helm. We understand that. This is how a windsurfer works. There is no rudder. Now what happens if if I shift this thing forward, if I shift the entire sail forward, you can't do that on a sloop, but you can on the windsurfer. What happens? Well, now then, you would discover that this force now comes over here, so there is going to be a moment, a distance here, which means there will be a turning moment like this. Which means on a windsurfer, if you simply move the sail effort forward, the boat will turn downwind. If I move it back, that means this force now goes back here, which means now there is a moment this way, which means it would tend to turn in this direction, which means that it would go upwind. This is the way you control a windsurfer. If I go forward, the boat's going to turn downwind. If I rig it back, it'll go upwind. But we don't do that on our boats, because our masts are fixed. But do you understand that bit? And that's the reason why you don't need a rudder. Now what you can do on a sloop, instead of changing the mast forward, you can change the relative pressure on the jib versus the main. If I keep the jib nice and tight and I ease the main, it's the same thing as moving the sail forward, because the center of effort now is going to be dominated by the force of the jib, not the main, which means the boat will go off the wind. If I want to go upwind, I do the opposite. Take the pressure off the jib and put more pressure on the main, and now then that's the same as moving the sail aft and the boat will turn up. A lot of schools will have you sail dinghies without a rudder, so you understand that. Have you guys done that?
I love rudderless sailing. It's so fun.
Yep. And so if you can do that, then you can windsurf.
Yeah.
But there is one further complication here which really makes it interesting. What is the effective heel on these boats? Because right now we're looking straight, we're looking at a boat that's not heeling at all. It's just sitting straight up in the water. We look at some in a moment. But what happens when it starts to heel? What happens to the center of effort here? If you look about in the, let's see, this would be the Y. So if we look at it in the Y direction, now then, this center of effort is shifted way over to here. Which means now then, there's a force going this way, which is going to tend to turn the boat this way. Which means that now then, the more it heels, the more it wants to go into the wind. Because the center of effort moves further and further this way, which means that this turning moment, because I take this vector here, and I put it on this direction here, it gets a longer and longer lever arm to turn the boat to windward. So anytime a boat heels to leeward, meaning away from the wind, like it normally would, then the boat will want to turn upwind. That's called weather helm. And it's an important feature for any designed boat because we want it to do that. And the way you counteract that is you have to pull on the tiller like this. As the boat heels, you pull in there, which then creates a force this direction, which then neutralizes the turning moment caused by the boat. So you can have a boat perfectly balanced, but as soon as it starts to heel, you're going to have to put in some rudder to keep the sum of moments equal to 0. Otherwise, it will turn on you. So this is a very important consideration to understand. Now, the other thing that you should understand is that, remember, this force here component is what's causing heeling force to begin with. This force here is coming from here. So understand that the force on the keel is also trying to cause you to heel. You have a force moment here, because this force is displaced in depth from this force, which means that these forces are also trying to tip the boat over. And the only way you can correct that is by having your bum here, your center of gravity here, to create a moment that's going to turn like this. You have to have a counter moment to counter the heel of the boat. And so the heeling complicates this balance problem quite a bit. And again, if you think about, we're used to always having boats that lean away from the wind. Windsurfing is quite the opposite. The more wind you get, the more you'll find that you pull the sail into you. The sails will be heeled to windward. And that's so that your weight is there to hold them up. And you'll find that when windsurfers go very fast, the sail is this way, which means that it would tend to want to turn the boat further downwind. But because there's no centerboard, this force here is only reacted by the skeg on a windsurfer, which means that they balance again. Because all of your effort is going to be right here on the back. When you heel it this way, it's going to want to turn in this direction. And that is going to be counteracted by that one little bit there which works. Yep. So, about that? Yeah, probably no questions about that. No, please understand this, you want to be able to talk in smart words when you see boats like that. And we'll see you next week. But again, I think that you cannot be a complete sailor until you've windsurfed. Because this really does teach you, if you really understand the physics associated with sailing. Yep.
Professor,
Yep.
is that a Garmin Fenix watch?
This one?
Yeah.
Epic. Epic.
Yeah.
You have one?
No, I'm looking to buy one right now.
I like mine a lot. The main reason why I've had like 3